Welcome to The Explainer. I'm Dr. Kem, and today we're decoding one of the absolute most fascinating molecular mysteries of our universe. We're going to explore how scientists use light to quite literally see the invisible. I know, it sounds a bit like science fiction, right? But this is actually the foundational tool of modern chemistry and physics. Here's a quick look at our syllabus for today. We'll be covering 1. Spectroscopy, 2. The electromagnetic spectrum, 3. Key terms in spectroscopy, 4. Principles of absorption spectroscopy, 5. Major types of spectroscopy, and 6. Applications of spectroscopy. Let's just dive right in. Starting off with Section 1, Spectroscopy and the interaction of light and matter. Before we get into the heavy mechanics, we really need to define exactly what this word means. Now, there's a critical distinction here that we absolutely have to get right. It's crucial to understand that spectroscopy is the theoretical science. It's the study of how electromagnetic radiation interacts with matter, atoms, molecules, ions. It doesn't actually generate any results on its own. It's just the underlying physics. Spectrometry, on the other hand, is the practical application. That's where we actually take a physical device, a spectrometer, to measure particular compounds and get tangible results. A good way to think about it is that spectroscopy is like the sheet music, and spectrometry is the instrument actually playing the song. Okay, moving to Section 2, the electromagnetic spectrum, which is essentially our universal ruler. To really understand these interactions, we have to look at the invisible energy all around us. All spectroscopy relies on electromagnetic radiation. Think of this as an enormous scale. On the low energy end, we have radio waves. These interact with nuclear spin, and actually, that's exactly how MRI machines at the hospital work. As we move up in energy, we pass microwaves, infrared, and then we hit this tiny, tiny sliver of visible light. It's kind of mind-blowing to realize that all the beautiful colors we can see in the universe make up less than a fraction of a percent of this entire spectrum. Moving past visible light, we enter the high-energy stuff: ultraviolet, X-rays, and finally, gamma rays. This whole range is essentially the ultimate toolkit the universe gives us to probe matter. And what's really wild is how this specific amount of energy completely dictates the interaction. The effect on matter depends entirely on the energy level of the radiation. For example, highly energetic radiation like UV and X-rays, they pack such a huge punch that they can literally eject an electron completely out of a molecule. But if we use radiation from the infrared region, well, it has much less energy. It doesn't break things apart. It just transfers enough energy to cause the molecules to sort of vibrate and dance around. So every single wavelength has its own totally unique physical effect. Next up is Section 3, Key Terms in Spectroscopy and the Mechanics of Waves. Let's quickly break down the math scientists use to actually measure this light. There's an ultimate cheat code for understanding light energy based on the direct relationship between energy, frequency, and wavelength. The equation is E equals H times V. But the golden rule you really need to remember here is this: a shorter wavelength means a higher frequency. Because those waves are packed in tighter together, more cycles are hitting per second, which delivers much higher energy. This one simple mathematical relationship is the absolute foundation of all spectral analysis. Just to make sure we're totally clear on the terminology, let's define a couple of terms. Wavelength, which is often represented by the Greek letter lambda, is simply the physical distance between two successive waves, usually measured in meters or nanometers. Amplitude, on the other hand, measures how high or low that wave extends from its center resting position. If you picture the ocean, wavelength is the distance between the swells, and amplitude is how tall the wave actually gets. All right, Section 4, Principles of Absorption Spectroscopy. How does matter actually take in and release this energy? Well, it's basically two sides of the same coin. Absorption occurs when matter transitions from a lower, comfortable energy state to a higher, excited state. But, and this is key, it only happens if the energy of the incoming radiation perfectly matches the exact difference in energy between those two levels. It's literally like a lock and key. Emission spectroscopy is the exact opposite. This is when those excited atoms or molecules decay back down to their lower energy levels. And in the process, they release that extra energy by emitting radiation, or light. Now, when we want to measure that absorption, the foundational math relies on two distinct laws. First is Lambert's law. This tells us that when monochromatic light passes through a transparent medium, the intensity of the transmitted light decreases exponentially as the thickness of the absorbing material increases. Think of shining a flashlight through a thick block of glass versus a thin window pane. Then we have Beer's law, which states that the transmitted light decreases exponentially as the concentration of the absorbing material increases. Imagine shining that same flashlight through a glass of water, and then slowly adding drops of dark food coloring. The more concentrated the dye, the less light gets through. Together, the Beer-Lambert law is the universal foundation connecting absorbance to concentration. Moving to Section 5, Major Types of Spectroscopy. This is our analytical toolkit. Let's look at the actual instruments used in a lab. When you walk into a modern laboratory, you'll see how different mechanisms produce entirely different structural clues. For instance, X-ray spectroscopy ejects core electrons to reveal complex crystal structures, like DNA. Fluorescent spectroscopy relies on internal conversion, where a molecule absorbs light and emits it at a lower energy. It is so incredibly sensitive that it can literally detect single molecules. And then there's mass spectrometry, which actually shatters molecules apart just to weigh the fragments and reveal their underlying structure. It's like a microscopic jigsaw puzzle, and these tools give us all the distinct pieces. So what are these machines actually looking at? By leveraging these different instruments across the different regions of the electromagnetic spectrum, we can observe very specific physical motions. We can probe whether a molecule is undergoing an electronic transition, meaning it's shifting its electrons around, which we pick up with UV and visible light. We can observe molecular vibrations using infrared light, or we can even measure pure molecular rotation using microwaves. Every wavelength essentially probes a different kind of atomic dance. Finally, Section 6. Applications of spectroscopy and its real-world impact. Because honestly, why does all of this theory actually matter to us? The real-world applications are just staggering. This isn't just textbook theory we're talking about. This exact science is actively used right now all across the globe. It's used to detect and identify organic and inorganic compounds, and to sequence proteins and amino acids. Environmental scientists use it constantly to test water and soil samples for microscopic pollutants. In medicine, biological samples like blood and urine are rapidly analyzed using these spectral fingerprints. And incredibly, advanced spectroscopy is currently being used to assist surgeons in the real-time detection of cancer and brain tumors. So it is quite literally saving lives by shining a light on things we can't normally see. I want to leave you with this really profound takeaway from our source material that I think perfectly summarizes our explainer today. Spectroscopy is arguably the most powerful set of tools ever developed for understanding the molecular world, from the structure of a drug candidate to the composition of a star 10,000 light-years away. Just by analyzing how light interacts with matter, we unlock the blueprints of reality itself. So I'm throwing the question over to you, whether it's curing a complex disease, engineering a new sustainable material, or mapping the chemical makeup of a distant, undiscovered galaxy. The tools of spectroscopy make it all possible. Now that you know how light decodes the universe, what molecular puzzle would you want to solve? Thank you so much for joining me for this explainer, and keep questioning the world around you.